Hello everyone, welcome to this video. In this video, I'll talk about Eratosthenes. Eratosthenes was a Greek mathematician, geographer, philosopher, poet, writer, and a polymath basically. And so he was basically expert in several different fields. And some of his contemporaries were so jealous of him that they used to call him Beta, which is basically the second letter of the Greek alphabet. So what it means is that they used to say that, they spreaded this rumor that Eratosthenes is the second best in all this field he worked in. He was not best in any of this field. But if you actually, look at his work, it's very evident that he was the best in all of this field among his contemporaries. So, and also he was the librarian of the Great Library of Alexandria. So one day, Eratosthenes was reading a book on geography, and he read this interesting info that in a city called Syene, S-Y-E-N-E, Syene is a city it was a city in Egypt. In that city, on 21st of June at 12 p.m., a vertical stick doesn't cast any shadow. So what does it mean? Well, normally, if there's a sun out there, and if you put a stick vertically, there will be some sort of shadow here, right? But he read that in that city, Syene, at 12 p.m. on 21st of June, a vertical stick will not cast any shadow. Now, for any mundane people, any normal people, this information will seem very trivial, right? It will not bear a lot of importance. But Eratosthenes was not that kind of person. He was a true scientist. He thought about it deeply, and he asked the question. I mean, this is what scientists do. This is what a true scientist does. He or she asks question. So Eratosthenes asked, okay, what about Alexandria in my city? What will happen on 21st of June? Will a vertical stick, will it cast any shadow? And he experimented, and he found out that it's true. It does. I mean, in Alexandria, at 21st of June, if you put a vertical stick like that at 12 p.m., it will cast a shadow. Now, he was very baffled by this result, and he asked, okay, why this is the case? Why in Syene it doesn't happen? There is no shadow, but in Alexandria, a vertical stick casts shadow. What is the resolution of this conundrum? And the conclusion he found was that surface of our Earth is not really flat, it's round, right? So imagine if the surface of the Earth was flat, let's say if this is Earth, maybe a disk, right? A circular disk, and this is, let's say, flat, the surface is flat, and if this is, let's say, Alexandria, and this is Syene, and let's say this is Sun. Sun is obviously huge, and compared to Earth, I mean, obviously I didn't draw it proportionally. So let's say the sun rays are coming like this. If they come vertically, then, and if there is no shadow in Syene, there shouldn't be any shadow in Alexandria either, right? But this is not what we are seeing. So the only resolution is that Earth's surface is curved. If it is curved, let's say like this, and then if this is, let's say, Syene, the sunlight will hit that place vertically, there will be no shadow. But whereas in Alexandria, for example, if it is here, it will come with an angle, and there will be shadow, right? Now this idea that the surface of Earth is round, it's not flat, it's not really Eratosthenes' idea. It was there for a long time before some of the other thinkers also thought about it. But still, there wasn't any conclusive agreement. Like some scholars used to think that the surface of Earth is flat, and some scholars used to think that it was round. But Eratosthenes went a step further. He found a very genius idea. So what he did was that he put that stick. Basically, this is in this figure. Let's say this is Alexandria. I denoted it with A, and this is Syene, that city. I denoted it with S, right? Now this is the stick. This is the small stick that he put, and he saw this is the length of the shadow. This part is the length of the shadow, right? And This is sunlight basically. Sunlight is coming, and this is the shadow that we are getting, and this is the length of the stick. And then he drew this diagram, which is quite fascinating diagram. From this diagram, he found out that this angle right over here and this angle right over here, they are equal. Now, what is this angle? This angle is basically the angle that is created. The angle is created by if you draw one line from Sin to the center of Earth and another line from Alexandria to the center of the Earth, you'll get this angle, right? So it's basically the city Sin and the city Alexandria. They make this angle at the center of Earth. So he found out that this angle right over here and this angle, they're equal. Why? This is very basic high school geometry, that if we have two parallel line and there is another line that crosses, that line crosses those two parallel line, then the alternate angles will be equal, right? So this angle will be equal to this angle. Sorry, this angle will be equal to this angle. These two alternate angle, they are equal. If you look at it properly, these are actually alternate angle. There's a parallel line. These two lines are parallel line, and these two angles are alternate angle, right? So they has to be equal based on our high school geometry theorem. They are equal. So he found this. He measured this angle. How? He measured this angle based on the length of the stick and the length of the shadow. He calculated this angle. He found this angle. And as he knows this angle, he also knows this angle because they are equal, right? And then what he did is he appointed a guy to measure the distance between Sin and Alexandria. And that guy measured the distance. So right now he has the distance, he has the value of the distance between Sin and Alexandria, which he found out to be 800 kilometer. And this angle that he found was actually, that he calculated, was actually 7 degree. Right? And that means this angle is also 7 degree. Now he has this, basically it's one of the portion of a circle, because our Earth it's round, and if you take a 2-dimensional slice, it will be a circle. So this is basically one of the portion of the circle, that circle, where we know this equation, S equal R theta, right? Theta is this angle, and R is the radius of Earth, and S is basically this segment here, this segment right over here, which he calculated to be, he didn't calculate, he appointed a guy to measure that distance, which is 800 kilometer, and he found out to be 800 kilometer. Now, so what he did is that from this equation we can write this equation like this. He wrote it like this: S equal to R equal to S over theta, right? Then if it is the case, and also for a circumference, what is the circumference of the Earth? If you write it as C, we know that C equal to 2 pi R. He also wrote it as R equal to C over 2 pi, right? So this is one equation that we got, and this is another equation. They has to be equal because both of them are R, right? So he wrote them like this. He wrote them like, okay, I'm going to write it here. He wrote them like S over theta equal C over 2 pi. And here he just plugged in all the values there. So from here, if we write it like this, C equal S over theta multiplied by 2 pi. And he put the value of S, which is 800 kilometer. And theta is 7 degree, but you have to use a radian. So if we want to convert a degree angle to radian, we have to multiply it with pi over 180, right? Multiplied by 2 pi. If you calculate it, which Eratosthenes apparently did, he found out that the circumference of Earth is 40,000 kilometers. And if you want to know what is the current estimation of the circumference of Earth, you'll be surprised, which is 40,075 kilometers. So basically what Eratosthenes did, he calculated the circumference of Earth with 99% accuracy from 2,200 years from now. 2,200 years ago from now. So my man Eratosthenes calculated the circumference of Earth with 99% accuracy 2,200 years ago from now, and his only equipment was a stick, geometry, and his brain. What an absolute genius.